Most people believe that noble gases are completely inert and that they never react under any circumstances. Xenon difluoride is one of the compounds that break this rule. In general, noble gas compounds have some interesting properties. Like most covalent inorganic fluorides, xenon difluoride is moisture sensitive. It decomposes on contact with light or water vapor. Xenon difluoride is a dense, white crystalline solid.
Xenon difluoride is a noble gas compound. And before we start talking about noble gas compounds, let's just talk about the basics. Xenon difluoride is composed of one xenon and two fluorides. Its molecular geometry is trigonal bipyramidal, comprised of 2 sigma bonds and 3 lone pairs. Because of the 3 lone pairs, its actual geometry is linear, with a bond angle of about 180. Xenon difluoride on its own is a strong fluorinating agent and has a bunch of other uses.
You can think of xenon by itself as an introvert and fluorine as an extrovert. Xenon prefers to be alone. You can usually find it on its computer or reading a book. Occasionally, xenon goes out to socialize with the fluorines, forming xenon difluoride. We call this interaction a noble gas compound.
Synthesis of xenon difluoride. 2 fluorine atoms and 1 xenon atom making 1 mole of xenon difluoride, which is solid. Basically, xenon difluoride is produced in a metal container, usually nickel, around 400 Celsius. So, in the container, 1 xenon gas reacts with 2 fluorine gas, which ends up 1 solid xenon difluoride.
Aside from the synthesis being fairly straightforward, it's also fairly cheap and easy to buy online. Just do a search and, well, there you go.
One question you may be asking yourself, xenon's a noble gas. Why is it that xenon difluoride is stable? Well, the best way to answer this is with molecular orbital theory, and first let's start with diatomic fluorine. The basic principle is that 8 orbitals go in, 8 must come out. And the bottom orbital will be the strongest bonding interaction, and the top orbital will give you the strongest anti-bonding interaction. Filling in all the orbitals will leave the anti-bonding interaction completely empty, and that is why we say that diatomic fluorine is stable. And now all we have to do is do the same thing with xenon difluoride, of course using the molecular orbital that we made from the diatomic fluorine. When comparing xenon's orbitals to the diatomic fluorine orbitals, things can get a little complicated. First of all, xenon has d orbitals, and the energy levels of xenon's orbitals are not necessarily the same energy levels of the diatomic fluorine orbitals. And in order to find out which orbitals are going to interact, you would have to check the symmetry of each orbital. But as long as we stick to the rules that we had before, we should be fine. So 34 spaces for electrons, meaning 17 orbitals in, and that means 17 orbitals out. And the very bottom is always going to be the most bonding interaction, and the very top is always going to be the most anti-bonding interaction. Filling up the molecular orbital with all the electrons, we can see that the very top, the most anti-bonding orbital, is still not filled, and therefore xenon difluoride is stable.
Now that we've talked about the stability of the molecule, let's talk about the reactivity of the molecule. Xenon difluoride is commonly used as a fluorinating agent. Among the fluorination reactions that xenon difluoride undergoes are oxidative fluorination, reductive fluorination, aromatic fluorination, alkene fluorination, and radical fluorination. Xenon difluoride is also selective about which atom it fluorinates. For example, it fluorinates the arsenic in trimethylarsine but leaves the methyl group untouched. The reaction drawn is trimethylarsine and xenon difluoride, which is used to produce difluorotrimethylarsine and xenon. Xenon difluoride will also oxidatively decarboxylate carboxylic acid to produce a fluorine group, carbon dioxide, xenon, and hydrofluoric acid. Xenon difluoride can also be used as an etchant to remove silicon. This reaction produces xenon and tetrafluorosaline. At the end of all these reactions, xenon gas is always produced.
Relating back to the analogy, when xenon difluoride is combined with other things, xenon will leave the group and go back to being by itself.
Hi.
Hello.
How are you?
I'm good, thank you.
Yeah. So, why do you think that xenon fluoride is useful, and what is simple way?
Um, well, it has a lot of applications as an etchant because it will react with silicon, but it will not react with silicon dioxide because it's an oxidizing agent. It's very selective that way, so it has a lot of applications. As with like nanotechnology, MEMS, micro electromechanical systems, basically making very small, tiny machines. So it has a lot of, and it's fairly cheap compared to some other kind of etchants. So you could make like transistors maybe for cheap, stuff like that.
So then, what would be future application of xenon difluoride?
Okay, so I think the biggest thing is that a recent discovery is under very high pressure. Xenon difluoride will shift into a different lattice phase. Basically, we'll go into like a metallic phase when the atoms are basically like forced closer together. So what happens there is basically it turns into like an ultra battery. At least that's what they're calling it an ultra battery. So like basically, it can store a lot of charge. I think something like 1 kilojoule per gram of it. So it's very, very efficient. It basically all the energy that you put into it, it can exert that back out as thermal energy almost like 100%. So it's very promising, but it's still definitely in its infancy.
Nice. That's all I have for today.
All right, well, thank you.
So, xenon difluoride is a very interesting molecule. It also has current application as oxidizing and fluorinating agent. Unlike organic molecule, such as antihistamine, it has more potential source for future application. So,
In conclusion, xenon difluoride is a molecule that could change the world.
And that's science.